Hello student, I am Dr.A.K, Professor of Chemistry. Today I will continue from the last class, that is types of point defect. Last class I have discussed imperfection in solids. Imperfection in solids I have given idea. Now I will continue types of point defects. Point defects, already I told you, point defects are the irregularities. Point defects are irregularities, or you can tell deviations from ideal arrangement around a point or an atom. Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance. Whereas the line defects, what is the line defects? The line defects are the irregularities or deviations from ideal arrangement in entire row of lattice points. Okay. Thus irregularities are called crystal defects. Irregularities are called crystal defects. Irregularities in arrangement of ions or molecules or atom. Types of point defects. Now I am going to discuss. Point defects can be classified into three types. First, stoichiometric defect. Second, impurity defects. And third, non-stoichiometric defects. Three types. First, stoichiometric. Second, impurity defects, and third, non-stoichiometric defect. One by one I will tell you. Question is asked, hence listen carefully. Stoichiometric defects, what is this? These are the points defects that do not disturb the stoichiometry of the solid. Means they will not disturb stoichiometry of the solid, means arrangement of the solid. Some defects are there, not fully, it is not disturbed. They are also called intrinsic or thermodynamic defect. Two names are there. This is also called intrinsic or thermodynamic defect. Basically, these are of two types. Stoichiometric defect is of two types. First type is valency defect, and second is interstitial defect. Stoichiometric defect is of two types. First, vacancy defect, and second interstitial defect. What is vacancy defect? When some of the lattice sites are vacant, the crystal is said to have vacancy defect. Correct? When some of the lattice sites are vacant, then this crystal is said to have vacancy defect. This results in decrease in density of the substance, because vacancy is there, empty place is there, that's why decrease in density. Correct? decrease in density of the substance. This is the important point. Question is asked. This due to the vacancy defect, this results in decrease in density of the substance. This defect can also, you can say, develops when a substance is heated. When it is heated, then this defect also develops. When means vacancy defect develops when substance is heated. This objective type question they are asking this question. Then this I told about the vacancy defect. Actually density, you know, density is equal to mass by volume. Then this will decreases in density due to this void, you can tell, or empty place, you can tell, or vacancy, you can tell. Means gap will be there between the arrangement, some gap will be there. Then what will happen? That it affects the density. Its density is equal to mass by volume. Correct? Then density decrease means what? Mass will be less. Mass will be less and volume will be more. Correct? Because volume will be as it is, but that place in the arrangement some atoms will be not there, gap will be there. Then mass will be less, but volume will be same. Volume will be the same, but mass will decrease. Correct? That's why density is equal to mass by volume. The mass is less, volume is as it is. That's why it decreases. Density decreases. Now come to the intrinsic defect. What is intrinsic defect? When some constituent particles like atom or molecules occupy an interstitial side of the crystal is said to have interstitial defect. Means between the atoms some other atom will come. Which in that is not its place. That is not its place. Simply between the two atoms or two molecules, simply another atom or molecule will come without its place. Just like you can tell that in train seat is that in one bench, suppose 4, it is made for 4. Now 5 will come. Then what will happen? It is a place for 4, 5th has come. Or it is a place for 3, 2, 3rd will come. If it is place for 3, 4th will come. That is called interstitial. They will adjust, okay, between the two. That is called actually interstitial defect. Okay, interstitial defect, when some constituent particles like atoms or molecules occupy an interstitial site, the crystal is said to have interstitial defect. Okay, this defect increases the density of the substance. Density of the substance will increase. Now understood the reason. Now some extra atom or molecules has come. Then mass has increased, volume is the same. Then density will increase. Then this vacancy and interstitial defects are, or you can say this vacancy or interstitial defects, you can say what I have discussed, that that is shown by non-ionic solids. Who will show this defect? Vacancy or interstitial defects, that is coming under the point defects. Then this type of defect is shown by non-ionic solids. Non-ionic solids. Okay. Ionic solids must always maintain electrical neutrality, means positive and negative must be equal. Okay, that is the ionic, but non-ionic they will not maintain this neutrality. Ionic solids must always maintain electrical neutrality rather than simple vacancy or interstitial defect. They show these defects. Okay, means a non-ionic solids will show these defects, vacancy or interstitial defect. It is shown by non-ionic solids. Okay. Now this defects I am talking about, these two defects, vacancy or interstitial. Vacancy or interstitial defects, they show these defects as Frenkel and Schottky defects. Okay, this name has been given for this vacancy or interstitial defect. Their name is given separately. Okay, then what are their name? Then they show, means non-ionic solids. Only this will show vacancy or interstitial defect. Then they show these defects as Frenkel, name of the scientist, Frenkel, 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 and Schottky defects, Schottky, Schottky defects. Okay, I will try to send this diagram on this also. Then in vacancy defect, you know that in arrangement, suppose A, B, like that arrangement should be. But what you will find in somewhere, A is there, B is not there, again A is there, again B, again A, again B, again A, again in the middle somewhere A will be not there, again B will be there, again A, B, like that way. Then somewhere there will be a gap. Okay, this you should understand. Then this two types I told you, Frenkel and Schottky defects, is related to that. Then now I am talking about the Frenkel defect. Question is asked, concept is the same. This defect is shown by ionic solids. Okay, this defect, Frenkel defect, is shown by ionic. How I am telling you, the smaller ion, which will be the smaller ion? Then cation. It is shown by ionic solids. Then ionic cation and anion will be there. Then cation will be a small or anion will be big. Okay. The smaller ion, that is the cation, is dislocated from its normal site to an interstitial site. It creates a vacancy because cation is small and anion is big. Sometimes because it is small, it will dislocate, means from its original place it will go to the other place. In the interstitial, means between the other two, it will go and adjust. Then one vacancy is created because that left their original position and it went to the interstitial sites, means between the two molecules or atoms. And then one vacancy is created. Then this is a vacancy type. Vacancy, you can say defect, vacancy type, defect type. Okay, it is like that way only. It creates a vacancy defect at its original site and an interstitial defect at its new location. It will go to the new location, interstitial sites. Frenkel defect is also called dislocation defect. Another name is dislocation. You know already, because it is dislocated, that's why it went to the other places, interstitial sites. Hence another name is dislocation defect. It does not change the density of the solid. Question is asked. Direct vacancy effect and this that's a stoichiometric defect and non-stoichiometric defect. Then non-stoichiometric you have seen this particularly in that non-stoichiometric two types are there, vacancy defect and interstitial defect. Then in vacancy defect there will be decrease in density and in interstitial there will be increase in density. But here in Frenkel what will happen? It does not change the density of the solid. Question is asked. Okay, question is asked in all examination. In Frenkel defect, you can say density of the, it will not change. It does not change the density of the solid. Frenkel defect is shown by ionic substance. This question is also asked, in which there is a large difference in the size of ions. Cation and ion will be there. If a size difference is more, means cation will be very small and anion will be bigger comparatively, then there it will happen. There this defect will arise. Example I am talking about, because question is asked, they will give example. Correct? Then this example I am telling you that ZnS, zinc sulfide. Zn is a small size, sulfur is a big size. You know. Another example is silver chloride. Silver is a small, chloride is big. Silver bromide, same reasoning. Silver iodide. This will happen due to a small size of Zn and silver ions. Both are cation. Now come to the Schottky defect. A Schottky defect will create now this here what I have discussed in these things in intrinsic defect, like that situation will be there. It will go to the intrinsic sites. A Schottky defect I am telling you. It is basically, this is also a vacancy only. This is also a vacancy. But now see the differences. A Schottky defect, what is this? It is basically a vacancy defect in ionic solid. It is also in ionic solid. Both are in ionic solid. Okay, and pure vacancy is, already told you, pure vacancy. These things. I told you that these things, interstitial defect means under the vacancy defect, I told you that there are two, interstitial defect and this vacancy and interstitial defect, that is coming under the point defect. Then I told you one this non-ionic solids vacancy and interstitial defects that is shown by non-ionic, but these two defects are shown by ionic. Frenkel and Schottky defect is shown by ionic solids. In order to maintain electron neutrality, electrical neutrality you can tell, in order to maintain electrical neutrality, the number of missing cation and anion are equal. Here important thing is that this is also vacancy defect, but here what will happen in a Schottky defect, that cation will also misplace, anion will also dislocated, both will be dislocated. Suppose two cation is dislocating in the crystal, two cation positively charged, and suppose again two negatives are also dislocating, then now there is a neutrality, cation and anion, positive negative charge both are in equal number, dislocated, then there will be no effect on, you can say, charge, it is a neutral, because two positive, two negative dislocated. Like that way, if numbers are same, dislocation, cation and anion are dislocating and their numbers are same, then it will be neutral, means it will maintain neutrality, means electrical neutrality it will maintain. Okay, the number of missing cation and anions are equal. Okay, I will try to send diagram for this also. Like simple vacancy defect, a Schottky defect also decreases the density of the substance. Here you can see differences are there. In a Schottky defect also decreases the density of the substance, but what I discussed Frenkel, in Frenkel no change, density will not change in Frenkel, but in Schottky density will change. Question is asked. Okay. Number of such defects in ionic solid is quite significant. This type of can say defect is common. Number of such defect, how many defects will be there? The number of defects in ions, you can say such defects in ionic solid is quite significant. For example, in NaCl, sodium chloride, there are approximately 10 to the power 6 Schottky pair per cubic centimeter at room temperature. Actually, in NaCl, there are approximately 10 to the power 6 Schottky pairs per cubic centimeter at room temperature. In 1 cubic centimeter, there are about 10 to the power 22 ions. This also you should remember that in 1 cubic centimeter, there are about 10 to the power 22 ions in 1 cc. Okay, there are about 10 to the power 23 atoms. And how many defects are there? Then 10 to the power 6 Schottky pair will be there, defects. Okay, this you need the 10 to the power 6 out of 10 to the power 22, 10 to the power 26 Schottky pairs per cubic centimeter defect will be there at room temperature. Okay, room temperature 10 to the power 6 Schottky pairs will be there, means defects. Okay. Then here what you will conclude? Thus, there is a 1 Schottky defect per 10 to the power 16 ions. Okay, means every 10 to the power 16 ions, 10 to the power 6 are defect. Thus there is one Schottky defect per 10 to the power 16 ions. 10 to the power 16 and plus 10 to the power 6. How much? 22. 16 plus 6, 22. Then every 10 to the power 6 ions, you can say one Schottky defect will be there. Okay, means 10 to the power 6. This pair 10 to the power 6 Schottky pairs per centimeter cube. This question is also asked. Okay. Schottky defects per 10 to the power 6 ions. Already I told you. Schottky defect is shown by ionic substance. This is also shown by ionic substance in which the cation and anions are almost similar size. Here differences you see. In Frenkel, cation and anion, there was a more difference in size. But here both should be almost equal. Okay. Ionic substances in which the cation and anions are of the almost similar sizes, there this can say defect will be shown. Example, I am telling example. Because question is also asked. There so many theoretical question is asked from this chapter. Okay, numericals plus theoretical question also. Then here example I am telling you, NaCl. If you can say where then example, first example I told you NaCl, sodium chloride. Second example is potassium chloride, KCl. Third example CSCl, just like NaCl, CSCl, cesium chloride, sodium bromide. Then these are the examples of can say ions where cation and anions are of equal size. That is a different question. That question may be asked in this way also. Equal size cation and anion plus this also Schottky defect. Schottky defect is shown in NaCl, KCl, cesium chloride and silver bromide. And also it may be understood or you can note down this also, that silver bromide is very very important thing I am telling you, that silver bromide shows both Frenkel as well as Schottky defect. Correct? This is again important question. This silver bromide shows both Frenkel as well as Schottky defect. Question is asked. Okay. Now I am telling you another impurity defects. Okay. What is the impurity defects? Then by name it is clear that some impurity will be present there. With main molecules, some impurities will be there. Okay. Then now I am telling about the impurity defects. If molten NaCl containing a little amount of strontium chloride, SrCl2, suppose NaCl is the main. If molten sodium chloride, NaCl, containing a little amount of strontium chloride is crystallized, some of the sites of sodium ions are occupied by strontium ion, Sr2 plus. Suppose you have taken in molten NaCl, melting condition, in melting condition I am talking about. In molten NaCl containing a little amount of strontium chloride, SrCl2, and if it is crystallized, some of the sites of the sodium ions are occupied by strontium Sr2 plus. Each Sr2 plus, because it has a 2 positive charge, Sr2 plus replaces 2 sodium ions, because one sodium ion has 1 positive charge. Then it can you can say occupied by, means 1 strontium Sr2 plus ions are occupied by strontium 2 plus, means 2 sodium plus will be replaced by 1 strontium, because strontium has 2 positive, sodium has only 1 positive. Okay. Then some of sites of sodium ions are occupied by strontium 2 plus. Each strontium replaces 2 sodium ions. It occupies the sites of one ion and the other site remains vacant. Wherever strontium will be there, then one is that itself strontium, then in the place of sodium strontium is there, then it will cover 2, then one will be vacant, one itself. Then here 2 sodium, where 2 sodium could have accommodated, now only 1 strontium is there and 1 vacant site will be there. Correct? This is important here. It occupies the site of one ion and the other site remains vacant. The cationic vacancies thus produced are equal in number of that of the strontium ions, because how many this type of vacancy will be there, then wherever 1 strontium is there, one vacancy will be there. If suppose 20 are there, then 20 vacancy will be there, because near that strontium 1 vacancy will be there. Okay. Then their number will be, vacant number will be equal to strontium, number of strontium ions. Another similar example you can understand that is the solid solution of cadmium chloride CdCl2. Cd is again 2 positive charge, cadmium, CdCl2. Obviously Cl2 is there, 2 chloride ion, then cadmium will be 2 positive. There also it can be consider this cadmium chloride and silver chloride. If it is with cadmium chloride is with silver chloride, cadmium chloride is present in silver chloride, then there also you can say impurity defect will arise. Obviously other things are there. In one case, in case of NaCl, strontium chloride, strontium was there, and here with silver chloride, cadmium chloride is there. Okay. This again I will try to send you can say diagram. Now I am telling you other defect, that is the non-stoichiometric defect. Non-stoichiometric defect. This defect, the defects what we have discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of non-stoichiometric inorganic solids are known, which contain the constituent element in non-stoichiometric ratio due to defects in their crystal structure. These defects are of 2 types: metal excess defect, and second is metal deficiency defect. Okay. large number of non-stoichiometry inorganic solids are known, which contain the constituent elements in non-stoichiometric ratio due to defects in their crystal structure. Then I told you there are two types. These defects are of two types: metal excess defect and metal deficiency defect. Excess and deficiency, both type of are there, two types. And first type I am telling you, metal excess defect. What is the metal excess defect? By name it is clear that metal ion will be more, means cation will be more, excess. What is required? More than that is present. If more than that, what is required? Cation, anion, only this number you want. If more cation is there, then that is called metal excess defect. Metal excess defects this will happen due to anionic vacancies. Anionic vacancies, that in arrangement, if somewhere anions are not there, less number of anions, then obviously actually both should be equal, cation and anion, but anion vacancies are there, then obviously cation will be in excess. Then alkali halides like NaCl, KCl show this type of defect. Okay, question will be asked. NaCl and KCl show this type of defect. When crystals of NaCl are heated in an you can say atmosphere of sodium vapor. See, NaCl you have taken, sodium chloride, and you are heating it. This NaCl, you know, it is solid. If suppose you are heating NaCl in presence of or in the atmosphere of sodium vapor, then what will happen? This sodium vapor is extra. Sodium chloride, in that you have seen NaCl, Na plus Cl are there in equal number. But now if you will heat it in presence of sodium vapor, in the atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. Sodium vapor, where it will go? Then it will deposit. Sodium vapor, that is in sodium vapor, sodiums are there. Then sodium atoms are deposited on the surface of crystal. Okay, the chloride ions, diffuse to the surface of the crystal. Okay, the chloride ions diffuse to the surface of the crystal and combine with Na sodium atom to give NaCl. Means that now you are heating NaCl in presence of sodium vapor, then sodium vapor will deposit on the surface of NaCl. Then this from the NaCl, that chloride ion will come up and it will combine with Na plus and it will for NaCl. Then now this, due to this chloride ion, Cl minus vacancy is created because it went with the new sodium. Then due to that chloride ion, vacancy is created. This is the main things here. The chloride ions diffuse to the surface of the crystal and combine with sodium atoms to give NaCl. This happens by loss of electron by sodium atom, because sodium was only sodium in the form of atom. But now that sodium, when when sodium will lose its electron, one electron, only then it will form Na plus. And when Na plus will form, that Cl minus will go there. Then this electron, what will happen to this electron? One electron. Then now you have to think for this electron. This happens, I told you, this happens by loss of electron by sodium atoms to form sodium ions. The released electron diffuse into the crystal and occupy anionic sites where chloride ion left from the place where sites from the you can say sites from where chloride ion left, there this electron will go. Okay, means in the place of chloride ion, now electron went there. The anionic sites occupied by unpaired electrons are called F center. EF. Only at that point is called where electron went, that is called F center. What do you mean by the F center? Actually, it is this F center came from the German word for benzene inter. For FOR BENZENTER. For benzene, same spelling you can write. Benzene. TER you can write in the end. For benzenter. It is called for benzenter. For benzenter. But the spelling is FAR, benzene and TER. For benzenter. And this is for color center. For the color, for benzenter means you are talking about the color. Color center is called for benzenter. Then that is the F. Here that electron, where electron went, in the place of chloride ion electron went, then that center is called F centers. Question is asked. Okay, what is the F center? They impart yellow color to the crystal of NaCl. Okay, this electron, one electron went to the chloride position site, then this provides yellow color. They impart yellow color to the crystal of NaCl. If you see the sodium chloride crystal, then it will appear yellow. This again question is asked. The color results by excitation of these electrons when they absorb energy from the visible light falling on the crystal. It will appear yellow. I told you yellow color will appear, but when it will appear, then when visible light will fall on this, when visible light like ordinary light what we are facing daily, then in that when that light will fall on this sodium chloride, then it will appear yellow color. Okay, due to the visible light falling on the crystals. Similarly, excess of lithium makes lithium chloride LiCl just like NaCl, LiCl. Then excess lithium makes lithium chloride crystal pink color, PINK, pink. Because same way in NaCl you have heated with Na, like that way LiCl, lithium chloride, if you heat in the presence of lithium atmosphere, then extra lithium will be there, then it will look pink. And one more thing I want to tell you here, excess of potassium makes KCl. Now KCl, potassium chloride, you are heating. Potassium chloride you are heating in presence of you can say potassium. In presence of potassium, you are heating potassium chloride. In the atmosphere of potassium, you are heating potassium chloride. Then it will look violet. It will look violet color. Okay, violet color. That is also called lilac, L-I-L-A-C. L-I-L-A-C, lilac color. That is called violet. Then KCl appears violet. LiCl appears pink. And sodium chloride appears yellow. Okay, these questions are fit for medical. Fit for medical. Okay, even for engineering also, in main they can ask, other UPSC also it can be asked, because in UPSC sometimes a general type of question they will ask, but your IIT medical pure question, chemistry full deep question they are asking. Okay, then this I have told about the metal excess defect. Metal excess defect. Okay, metal excess defect due to the presence of extra cation. Due to the presence of extra cations at interstitial sites. This already I told you that this happens due to the excess cations. Then metal excess defect due to the presence of extra cations at interstitial sites, that I am telling you. Okay, same things are there. Zinc oxide, ZnO. Zinc oxide is white in color at room temperature, because actually why we are using room temperature, because when temperature will increase, many things will increase, change. Okay, temperature has a big role in appearance. Then ZnO, zinc oxide, is white in color at room temperature. On heating it loses oxygen and turns yellow. ZnO, actually it is a white color. Zinc oxide is a white color at room temperature, but on heating it loses oxygen and turns yellow. It loses means ZnO will convert to Zn plus half O2. Half O2, Zn plus means 2 plus, Zn2 plus half O2. Then plus 2 electron, means because Zno broken into 2 parts. The Zn became plus 2, Zn plus. Then 2 electron is that, plus 2e. Zn plus half O2 plus 2 electron. Then now there is a excess of Zn in the crystal. The Zn ion you have heated, then now what will happen? There is a excess of Zn in the crystal, and formula how will you write? Actually ZnO formula, suppose you have to write. If you are talking about this excess metal ion or excess zinc, particularly zinc example I am telling you, then it is new type of things I am telling you. Just like you are writing simply ZnO, zinc oxide, you are writing ZnO, zinc oxide. But here ZnO means you are thinking one Zn is there, one oxygen is there. But in fact, a number of Zn atoms will be more than one because of excess Zn, excess metal ion. Now you can write the formula like that, Zn and down 1 plus XO. ZnO you are writing, but here if you want to write the exact number of Zn, then it will be more than 1. More than 1, not only 1, because this is the defect. This is a defect, excess. Metal excess defect. Then obviously metal ion is more. That's why you are writing, obviously it will be more than 1. That's why its correct formula is Zn 1 plus X. Zn and down you write 1 plus X, a small x, O, ZnO. Zn is 1 plus X atom. Why now understanding? Due to the defect, because due to the defect extra metal ion is there, extra. Correct? That's why you are writing here in a particular case Zn you write it Zn 1 plus x O. Okay, this I think we have understood the meaning of 1 plus x. The excess Zn ions move to this excess Zn ions move to interstitial site, and the electrons it will move to the neighboring interstitial sites, because here electrons are also there, Zns are also there. Then both will go to the interstitial site. Zn will also go to the interstitial sites, and electron will also go neighboring interstitial sites it will go. Okay, this I have told you about the excess that is the metal excess defect. Metal excess defect I have told you. Now I am going to tell about the metal deficiency defect. Second one, metal deficiency defect. Now see, deficiency, that was the excess, metal excess, now it is deficiency, means less. Then now I am telling about that, meaning you understood, the reverse of this. There are many solids which are difficult to prepare in the stoichiometric compounds, meaning in a regular fashion. Okay, there are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metals as compared to the stoichiometric proportion. Stoichiometric means here, just to understand, suppose NaCl, Na plus Cl minus, Na plus Cl minus, again Na plus Cl, again Na plus Cl. Suppose 1000 NaCls are there, and all are arranged in a proper way. Then you can tell it is in a stoichiometry, means a balanced way. Na plus Cl minus, again Na plus Cl minus, Na plus Cl minus, perfectly it is arranged. Then this is in a stoichiometry. But if in the middle in the gap is there, Na is not there, somewhere Cl is not there, suppose, then they are not called a stoichiometry. That is called non-stoichiometry. Okay, I think we understood the meaning of stoichiometry and non-stoichiometry. Then this I told you that it is very difficult to prepare the stoichiometric compounds, and this generally it contains a less amount of metal as compared to the stoichiometric proportion. A typical example of this type is ferrous oxide, FeO. You can take example. Common example is ferrous oxide, FeO, which is mostly found with a composition of here FeO you are writing FeO. Then here how many atoms will be there? FeO. In the underwear anybody will tell, oh, Fe is 1, oxygen is 1. But it is not like that. It is not like that. Fe is not 1, not 1.0. It is 0.95. 0.95, less than 1. And O is 1 complete. That's a deficiency is there. Deficiency. What was required? 1 complete one, it is not there. It is 0.95. And its exact formula is Fe down you can write 0.95 and O. Just like Zn-O. That was the excess, 1 plus x. Here 1 minus x you can tell our exact way, ferrous, that is the 0.95. Fe 0.95 O. That is the correct. Then this I told you. In crystal of APO, some Ap2 plus cations are missing. Missing, it means like that what was required is not in the same number. Some Ap2 plus is missing in APO are missing, and the loss of positive charge is compensated. How? And the loss of positive charge is made up by or compensated by the presence of required number of Ap3 plus ferric. Ap2 plus is called ferrous, Ap3 plus is called ferric. Then that is actually made up, that is compensated by the presence of required number of ferric ions. Then this I have told you about the metal deficiency defect. Okay. Now electrical properties are there, and electrical properties are, and magnetic properties, that I will discuss in the next class. Okay. Thank you.